Hi, this video is going to cover the linked list based queue. We're going to see how to implement a queue using some sort of linked list. So we're going to use the adapter pattern. Remember that an adapter is a container that uses a pre-existing container data structure to implement a new different interface. What we're doing in this video is a linked list based queue. So we're going to create a linked list based queue class that uses a linked list data structure to implement the queue operations, namely enqueue, front, and dequeue. We could use a singly linked list or a doubly linked list. We're going to analyze which one we should pick in a moment. Now we have to work out a design decision before we can proceed with code or pseudocode, which is the correspondence between parts of the linked list and parts of the queue. You might remember that we had to go through a similar exercise with stacks. The stack has a top location, and we had to decide if the top of the stack should be the front of the linked list or the back of the linked list. Well, we need to make a similar decision here. It's a little bit more complicated this time because the queue manipulates two ends, not just one end, the front, like a stack. The queue has two ends that get manipulated. The enqueue operation adds an element to the back of the queue, and the front operation gets the element at the front of the queue. Also, the dequeue operation removes the element at the front of the queue. So one operation deals with the back of the queue, two operations deal with the front of the queue, and so we need to work out where does the front of the queue go and where does the back of the queue go. Now, a linked list has two ends to it, a front and a back, and so there's two natural ways that we could make this correspondence work. We could say that the front of the queue is at the front of the list. That's sketched in the middle here. So at the top I have sketched a queue that contains 714 with 7 at the front because 7 is on the left. And if we say that the front of the queue is located at the front of the list, then 7 is at the front of the list and 4 is at the back of the list. The other alternative is we could say that the front of the queue is at the back of the list, and that's sketched on the bottom here where the front element 7 is at the back of the list and the back queue element 4 is at the front of the list. So the way that we'll make our decision is to do an analysis where we look at the asymptotic efficiency, meaning the big O expressions for these two alternatives, and we'll pick the one that makes for a more efficient data structure. Let's review the efficiency of linked list operations that are relevant to this. So remember that most of these linked list operations are constant time, but there's one exception that's linear time. So the front, push front, and pop front operations take constant time in both a singly linked list and a doubly linked list. The back and push back operations also take constant time in both kinds of linked lists. The one exception is the pop back operation takes linear time in the singly linked list, but constant time in the doubly linked list. That was one of the distinguishing features of the doubly linked list. So this will guide our decision. If we make the queue's front be the list's front, then all of these operations are constant time regardless of which kind of data structure we use. So to enqueue, you would push to the back, which is constant time regardless of singly linked or doubly linked. To get the front, you would call the front operation, which is constant time for both data structures. And to pop the front, to dequeue, we would pop the front, and that's constant time for both kinds of lists. Now, the alternative is we make the queue's front be the list's back, and that would slow things down. So then, in order to dequeue, you would need to pop back, and pop back is linear time in a singly linked list. So the decision is we should make the queue's front be the list's front, because if the front of the queue is the front of the list, then all of the queue operations can be implemented in constant time for either kind of linked list. And if there's no advantage to using a doubly linked list, then we prefer the singly linked list because singly linked list has better constant factors because it has fewer pointers in it. So part of our decision will be to use a singly linked list here. So just to memorialize it here, here's our decision. The front of the queue is the front of the list. So if I have a queue that goes 714 with 7 at the front, then I'll have a singly linked list with 7 at the front. All right, now let's get into code now that we've made that decision. So here is my template class, linked queue. The private data member is just a singly linked list of T elements. That's all we need because we're doing an adapter data structure. The default constructor works fine. That makes an empty linked queue. And the size of the overall queue is equal to the size of the linked list, so that's a single line function. So we get to reuse these singly linked operations. The constructor is constant time, the size accessor are constant time. Those ones are pretty easy. Now let's look at enqueue. So enqueue adds an element to the back of the queue, And in order to do that, we add x to the back of the linked list. So we do list.pushbackx. That's all there is to it. There's no error check needed here because you're always allowed to add an element to an empty queue. It doesn't matter if the queue is empty. And this takes constant time because the pushback operation is constant time in a singly linked list. Okay, now for the front operation, we check for an empty queue. You can't get the front of an empty queue, so if size is 0, we throw an exception for that. If we get past that check, then we just call the list front operation, and that's all there is to it. List front is constant time. DQ is also pretty easy. We say if the size is 0, then throw an exception because there is no element at the front to remove. Otherwise, we do the singly linked list pop front operation. That's all we have to do, and that takes constant time. So here's the summary of all these operations. Again, with this container adapter approach, we got a pretty simple data structure for a queue. It was pretty easy. Not a lot of new ideas there. And all of the major operations are constant time. The constructor that makes an empty queue, get the size of the queue to nqx, get the front of the queue, and dq an element at the front. Those are big O of 1 or constant time each.